We are going to do double integrals using polar coordinate system. Sometimes the region D, you know the region in the floor, the XY plane that you want to integrate, sometimes that is curved, especially like circles and bits of circles. But sometimes, do you know those little petal leaf things? Can you imagine how difficult it would be to integrate vertically upwards with a region D that was really better designed as a polar coordinate formula, right? So there's your normal double integral over some region D, but we're going to use X's and Y's. If you do polar on it, can you remember this? X is r cos theta, r is y r sine theta, and the dx dy gets replaced by a weird r that I'm not going to tell you where it comes from until we do Jacobians, and then I'll prove to you why you need it. Jacobians, by the way, is how do you do change in variable in a multivariate function? You know how like u equals x cubed plus 1, change a variable? How do you do it when there's two variables? They're called Jacobians, and that's where that guy comes from. So right now you've just been told it. And so you replace the dx dy integration variables by the new r and theta ones. That r I will forget sometimes. Watch me, because I shouldn't. And so the x's in your formula become, that's meant to say r cos theta. The y's in your formula become r sine theta. That's not very clear. And then you do an r dr d theta. So far, so good. Right. So let me show you a very simple example of that. Suppose the region D was a unit circle. And I wanted to integrate, right, my usual double integral over this region D of a very simple looking function. Let's do the y's first, dy dx, right? Now, if you had to do it with last week's technique, wouldn't you have to figure out some way of representing this region? And so you'd have to split it vertically or horizontally. If you split it with a vertical guy going like this, then it would go from -1 to 1. So I could do the integral from x equals -1 to x equals 1. Well, that's not too bad. But what about these guys? Well, if you rearrange this equation, you get y squared is 1 minus x squared. And that makes y plus the square root of 1 minus x squared. That's this one. And the lower one, y equals negative the square root of 1 minus x squared. So this integral will be from y equals negative the square root of 1 minus x squared to y equals positive the square root of 1 minus x squared. And then the x plus y, and the dy, and the dx. I'm only going to take this one step further to show you why this would not be a good idea. If you integrate this guy, you will get xy plus a half x squared, evaluated at these two places. And I should have called that guy y squared. Now, if you plug y into here, it's nice. But see, when you plug into here, don't you get x the square root of 1 minus x squared? Can you see how ugly the integrations get? The minute you start plugging these guys in, won't this turn into a horrendously ugly looking expression with some square roots of 1 minus x squares floating around? Very messy. So rather, question.
Yeah, that would just not be a good time.
Just, yeah, you would not have a fun time trying to continue this to the end. You'd have to do at least one new sub and some other messy stuff. So back to the same story. So we have x squared plus y squared equals 1, right? That's region D. Now, if you want to represent this in polar form, don't you do theta goes from 0 to 2 pi, and doesn't r go from 0 to 1? Are you comfortable that that represents this circle? You remember 0 all the way right to 2 pi, r value, because we're talking about, remember, the entire region, right? So that's why it's this. Now, if you want to set that integral up, it's going to be from 0 to 2 pi, and from r equals 0 to r equals 1. Now, the function is x plus y, so that's r cos theta plus r sin theta. And you get an r dr d theta. Now, I'm going to do a little bit more work on this. Can't I pull out an r from here? And so what do you get? You get r squared cosine of theta plus sine theta. And you have a dr and you have a d theta. Do you notice that this is a variable? You can separate the variables here. You notice that? That happens a fair number of times. So I'm going to do a theta to 2 pi and a 0 to 1. And this guy is going to be cos theta plus sine theta. And this guy is just going to be r squared. And that's much nicer integrations. Would you agree that those two integrals are really quite easy to do? And this one just, I know it's a mess, but it says cos theta, so you'll get sine theta. And this says plus sine theta, so you get negative cosine theta. And you'll evaluate them from 0 to 2 pi. Then you go times, and this guy's just 1/3 r cubed from 0 to 1. And this guy gets a third. And this guy gets you the sine of 2 pi, which is nothing. Take away the cosine of 2 pi, which is -1. Subtract another 1. Is that right? Theta.
Is the cosine of 2 pi still 1? Just 1?
Oh, yeah.
1?
That's it. I was wondering why I was getting 0 there.
But there's that minus in front, so that's why the negative.
Right, so the 2 pi is -1. Oh, yeah. And then when you plug it in here, it's just 1. So you get the negative of 1. So -2.
It would be the negative of the -1, because again, it would still be the minus with the 0.
Right.
Wondering-
I'm going to write that guy down. I should never try and do things in my head. You'd think I'd learn by now. So I'm just doing that guy again. This guy came out nice, so I'm not worried about that. It's going to be the sine of 2 pi, take away the cosine of 2 pi, subtract the sine of 0, take away the cosine of 0. And then everything gets times by a third. Okay, sine of 2 pi I do know is 0. Cosine of 2 pi I do know is 1. Take away. Sine of 0 I know is 0. Cosine of 0 I know is 1. The whole thing is times a third. This guy is -1. Oh, that's interesting. The negative of -1 is actually add 1 times a third. Oh, I was wondering about the 0, and I shouldn't. 0 is allowed for a double integral. I have mentioned that. Couldn't it just be a shape where half it is above and half of it's below and they're cancelling each other out? Yeah, okay, I'm cool with that. It worked out fine.
I mean, that's what we have here. Half of it's above the origin, half of it's below.
Oh, you've looked at the whole thing? I guess so. Yeah.
And if you think about the plane x plus y, OC
Yeah.
equals x plus y, it's probably going to split on the origin. So.
Right, so in one half it's bumping up, and the other half it's bumping down.
Yeah.
I guess 0 makes more sense than what I think about it. I think my brain was thinking too physical here. Like 0 wouldn't make sense because I was still thinking 0 is a volume rather than a volume underneath or above the XY plane, which is like the area above a curve, right? It's not always positive. You can get negative answers as well. So
There are sometimes you want to get a 0 answer. like when you're balancing forces, especially with like magnetic coils. You
You
want
would,
them to
yeah.
be
You want things to be, yeah. So in a way, zero is what you would want. Right. Here's a straight out of the homework. I'm going to probably have to pick a lot of their questions, because if you tweak them, they can be really ugly very quickly. And in this case, D is the top half of a disk. And a disk just means that guy. And what kind of disk? The radius in my disk is going to be 2. Your disk, it might be 3, 4, or 44. So this is the region, the disk D, that they're talking about. Oh, that's maybe why they're calling these things Ds. They're just calling the XY shape a disk. Nah, maybe not. This fella has to be written down in terms of limits for 0 and limits for theta. Now, when you're building one of these polar shapes, you always start, when you're thinking about the angle, with the x-axis, agreed? And in this case,
pi.
0 and finish at pi, agreed. Now, the R value for a circle is dead easy. If the radius is 2, the R value is going to go from 0 to 2. If you make it 2, you only get that bit, right? Make it 1.9, you get the next bit. So it's going to go from 0 to 2. Are you with me? Right. We're coming back to that question, but I want to spend a little bit of time talking about what the intervals for R and theta would be in other shapes. So imagine your shape was made like this. And the inside radius was 2 and the outside radius was 5. My thetas would still be 0 to pi, agreed? What would the range in the R values be in this shape now?
Well, you would want your R value to be from 2 to 5.
Correct. Okay. Now, the x equals r cos theta and the y equals r sine theta never change, right? As long as you're talking polar, right? Those never change, right? X will be r cos theta, all the y's will turn into r sine thetas. What about a shape that looks like this? Right.
Then the intervals of theta would be pi 6 to pi thirds, and then the interval of the radius would be 0 to 7.
Agreed. We'll take it one last ugly one. These same guys, right? So imagine these are the same. And it ends up being that region there. Wouldn't the only difference be the R values, the range of R?
You could have a really nasty one and have it be something where it's from, pi over 3 to, let me think here.
7/9 pi or something.
I was going to say
really?
2 pi, and then you'd want to add another 1/6 pi, so it'd be 13/6 pi. So it'd be the region that's all the way around the rest of the circle that you've cut out.
Right.
Like you
And then
think of what you made as a slice of cake, yeah.
Yes.
You do the rest of the cake.
Are we
Horrible.
yeah. Are we cool with these ones? Yeah. I mean, you could advance them. These shapes work really well, don't they? Because for want of a better word, aren't they circular in some sense? They have a circle thing going on. And circle things are good for polar. Right, so back to that question I've been ignoring for a while, which is this one. We've set up the region D. And so our integral is going to be from theta equals 0 to theta equals pi, from r equals 0 to r equals 2, 4 times r cos theta squared 1r sine theta. Then remember that r dr d theta. You know, can't emphasize it enough because I'll make a mistake. You know, isn't there a temptation just to say dr d theta? Because, you know, you think dx dy. Now, in this particular one, if you square that and you multiply that and you multiply by that, I believe you get 4, 1, 2, 3, 4r cubed cos square theta sine theta dr d theta. Does that look good?
Oh, why would it be r cubed?
There's an r squared here and one more here. Oh, it's r4. Are we happy with r4? Right. This would get you r squared. This is another r, so it's r cubed, and this r here gets you the fourth one. So 4r to the 4. Does that look good? Right. Can you separate this thing?
Yes.
So I'm going to do cos squared theta sine theta here, and that's going to go from 0 to pi. And this fella here is going to go from r equals 0 to r equals 2, and it's going to be 4r to the 4 dr. Right, at this point, I'm going to stop. Wouldn't you be able to integrate that just by a power series and get some ugly answer? I would have to do a little bit of work on that. Tell me the technique from Calc 2 that you would use to integrate this one.
That looks like that could be a u sub.
Correct. Who would the u sub be?
So you would be the cosine squared theta,
Not the whole cosine squared.
or just the cosine
You
theta.
would
Just the
be cosine.
Yeah. So can we just dot that? I think if I get to the Calc 2 step, can't I just dot it? Because I know you can do Calc 2 stuff. Right. Now, if you try to do this same question, but using, you know, x going from -2 to 2 and y going from 0 to the square root of, what would that be? 4 minus x squared. Can you imagine how horrendous the integral could be? In fact, sometimes the integral is not even doable, right? If I went and said to you, integrate x squared, the square root of 1 minus x squared, would you agree that you'd have problems? Because none of the techniques that you have would really play well with that one. So in a lot of situations, you have to do it by polar. It's just impossible to do it if you tried to do it with the x's and y's.
Professor, that last page you just took off.
Yes.
Let's see. It was the one with the circle, and it was x squared plus y squared equals 1. And it had the full circle on it. It equaled.
Yes.
So when you do the double integral, right?
Mm-hmm.
Would it be r cosine squared because x is equal to r cosine?
Well, the original function that tied along with was this one. This is the z guy.
Oh, okay. Okay.
So
Never mind then.
that's basically the x add y.
Gotcha.
Yeah.
Okay. Thank you.
And in this case, it was a square and a single because this was an x squared and this was the y. So this here would represent the x squared term and this would be the y. There's your 4x squared y.
Awesome.
Okay, let's have a look at our next guy in our list then. Nothing. Oh, I take that back. I was going to skip by 2 because it looked too obvious, and then I had another look and it wasn't. For no reason, they've decided to call this one an R instead of a D. I still don't have a good explanation for why they do that. It looks quite cosmetic to me. So this is a region, and oops, I better check it. The region R is the quadrant in the first quadrant, so it's in the first quadrant. Okay, that's important. It's made up of the interaction of a circle and the lines x equals 0 and y equals x. Wow, there's a lot going on in that one. Now, everything's going to happen in the first quadrant. So if I do x squared plus y squared equals 4, can you see I get a guy that looks something like that? Great. If I draw the line, maybe in different colors here, if I draw the line y equals x, it looks like that. And if I put in x equals 0, what do you get? What would x equals 0 be in this? I mean, it's a line, but what line would it be?
A vertical line at x equals 0.
Right. So when you, come on, pen, there you go. When you put that combination together,
Oh, why did you write a negative for the y?
I have no idea. I was thinking plus and minus 4 probably. Are you comfortable with this being the region, the way they described it? Circle, first quadrant, y equals x, x equals 0. Now, that becomes, in polar form, these two guys. Right. The r value would be 0 up to the edge. So I'd be comfortable with the r from 0 to 4 part. I need thetas from the red line to the vertical line. So
Not
they need to
comfortable
be
with the 4. It should be 2 because the equation has it as equals 4, which is the radius squared.
correct. Are we comfortable 0 to 2? Right, I was keep thinking of this guy. I should focus on everything. What's the angle here and then here? Because that's the guys we need.
It looks like it would be pi fourths to pi halves.
Okay. Small one first. Big one. Right. Now you said it looked like you want to convince me more that the reason why this angle is pi upon 4.
Because the line of y equals x goes directly through the center of our
Okay.
wedge.
So you're saying 45 and 45? Yeah. And there's a pi upon 4. Agreed? Right. Now, side issue. There is a way of finding out what that angle is. If you have any line, y equals mx, right? So it could be y equals 2x, a half x, or in this case, just x. And you want to know what this angle here is. I'll call it theta. Theta is the inverse tan of the slope of a line. Isn't that a helpful little property? So if you get a line and it's y equals 2x, right? Just like this is y equals x. Theta then is just going to be the inverse tan of 2. Okay, it won't be a very pretty number, but that's how you could do it. You might use that once, and that's it, but it's nice property. Well, we've set this guy up, I think. We're ready to go. The theta equals pi upon 4 to pi upon 2. The r goes from 0 to 2. The 4x becomes 4r cos theta. The y becomes r sine theta. And then you do the r dr d theta. And because I'm running short of room, I'm going to do two things at once. If you pull out r as a common factor and you multiply it by that r, can you see why you would get 4r squared? So this r times this r, and where's that 4 coming from? This r times this r, you get r squared. And you would get a 4 cosine theta, take away a sine theta on the other side. So this r and a common factor of r gets me r squared. The 4 cosine and the minus sign get you here. These two guys split, don't they? And now you have two calc 2 integrals to do. Are you okay with that shortcut? That I pulled out an R and then separated. A large number of these, have you noticed, always separate, which makes life easy. Not all of them do, but so far, every one that we've done has came out that way. So let's see if we can find something that doesn't separate. Not that one separates. Ooh, cool. Whoa. Right. We're back to D again. That's the original double integral. And D is described as a region bounded by the semicircle, that guy, and the y-axis. And this one had two features that kind of, this caught my attention as really weird looking. And this, because it's an interesting function. All right, now, can someone tell me that is part of a circle? But what would that equation look like if it was x squared plus y squared equals a number? That way I can get an idea of what the circle would be. What would that be?
X squared plus y squared equals 64.
Are you okay at looking at that and realizing this is what you get? Is that comfortable? So this time I'll get it right. Is it this a circle of radius 8? And since y-axis is also involved here, and they mentioned it's a semicircle, which means half a circle, if you put in the y-axis and you do half a circle, do you see it's that half? Because couldn't it have been this half or this half? And it could have been, but it's not that half. Why is it the right-hand half, but not the left-hand half? It's a subtle thing, but it's there.
Because x is positive.
Correct. If they'd wanted this side, wouldn't they put a negative there? Right, it would be negative the square root of this. And it's easy, you know, little details like that kind of disappear. So 8 up here, negative 8 down here. There's my region. And I'm going to do something a little bit different with the thetas. The radius is going to go from 0 to 8. That one was easy. And I am going to do that. Can anybody see why I'm describing theta in terms of a negative angle, negative pi upon 2, to positive pi upon 2? Why am I going that weird way?
Because if you did it as 3 pi halves, it would denote that you're going around from the left side.
Yes. If I'd said pi upon 2 to 3 halves, wouldn't I be describing the other half, the left side, as you described it, Sally? Yeah. So it is okay to have negative values of theta. In fact, sometimes you must have them. Now I'm just taking this one a little bit further and then I'm going to stop. So it's going to be an integral from theta equals negative pi upon 2 to theta equals positive pi upon 2. The r is going to go from 0 to 8 and the e to the x squared plus y squared r dr d theta. While I'm writing all this down, I want you to look at this and see if you can make it into something really nice and pretty.
You could factor out the r squared, then you'd have cosine squared theta plus sine squared theta, which is just 1.
So won't you get an r e to the r squared dr d theta? Agreed? And they are separating. And this might throw you, but hopefully it won't. Since there is only one variable present, you might have a bit of an issue of, well, what do I get for my d thetas? I can't leave something blank, right? I need something there because I've got to integrate it, right? And it's not 0 d theta. What goes here?
A 1.
Agreed? That makes sense. But if one of the variables disappears, like it's not there, that's a great sign you can separate them. And the one that's not there is really one thing, right? It's a 1. So it's one of these. So you get that. How would you tackle r to the e to the power of r squared?
That would be a u sub with the r squared being the u.
Agreed? And off you go in Calc 2. I like this stopping at the Calc 2. It means I can do more examples. 5's pretty similar. Oh, here's one. Question 6. And I'm going to need Desmos in a minute. The equation isn't in x's and y's anymore. The equation for the region D is this guy. And it talks about a rose. And it also talks about one petal. And you might say, well, what is the value of f of xy, right? The guy that you would typically be, working with. Well, he's just going to be 1. Because if you want to find the area of a shape, aren't you just finding the volume of the shape whose height is 1? So you imagine a petal and you made that height 1, wouldn't that number be the same as just the area of the petal? Now I'm going to have to find Desmos, so hang in there because who knows how long it'll take me to get the thing up and running. Is it here? Okay, it's got a chance of being here. Move that over there. Did I tell you about the guy who went to the doctor? I told you the joke about the guy that went to a doctor. I'm going to tell you that joke. It's in my head and it's going to bug me if I don't. Right. So a guy goes to the doctor and the doctor's looking kind of worried. And so he says, "What's wrong, doctor? I mean, give me the news. What's up?" And the doctor shakes his head and says, "I've got some good news for you. And I've got some bad news for you." So the patient said, "Okay, tell me the good news." So the doctor says, "You'll get 6 months to live." And he looks at him and said, "That's the good news." He says, "Yeah." So he says, "What's the bad news?" He says, "Oh, I should have told you 6 months ago." But the doctor says, "There's chance. All you need is a brain transplant." The guy says, "I've never heard of him." Says it's cutting edge, just out, really expensive. So the patient says, "How expensive?" Says, "Come on, I'll take you into this room." And there's 3 jars of brains. He points at the first one. He says, "These brains here are $2 an ounce." And the guy does a quick calculation. So that's pretty good. I can afford that. Says, "How come they're that cheap?" He says, "Oh, these are English professor brains. Get plenty of them. Dime a dozen. They're quite cheap." So he moves to the next table and says, "These ones are $20 an ounce." And the guy says, "They're a bit more expensive." Says, "Well, they have to be. These are mathematician brains. These are much better brains. $20 an ounce." So you go to the last table and he says, "What about these?" He says, "Oh God," he said, "these ones, $2 million an ounce." And the guy says, what on earth is, what kind of brains are these? The guy says, oh, these are politician brains. And he says, well, why are they so expensive? And he said, do you know how many politicians you have to kill to get an ounce of brain?
Terrible.
Oh, terrible good or just terrible?
I like that.
That's pretty funny. That's pretty true.
Okay,
Multi-layered joke.
it was. It gave me a chance to get Desmo set up a little bit as well. Okay, so I'm hoping that I've got Desmo set up properly. It's been ages since I've used Desmos to do polar, but I believe I should be able to get away with it. Let's hope so. If you do R equals 8 cos theta. If not, I think I'm thinking here, I know what to do here, but I need variables. If I got, where's the variables hiding? In functions? No. Scroll down. Try to find variables.
You can just
I
type in theta and
That
it'll
was what I was
throw it
about
in
to
for
say.
you.
Okay, so it's hidden somewhere. There it goes. You see our guy? I'm going to do a 0. Oh, good, it's found it. I'm going to go 0. I'm going to do 2 pi. Where in something? I'll just do pi. I'll probably understand pi as well. Tell me it understands pi. No.
A
Yes, that'll
lowercase
take you
p, I
by.
think.
What? Say it again.
Lowercase p.
Okay, pi. There we go. Okay, here's the shape. That is not the shape that I was expecting to see, because this shape should have petals. And it is r equals a cosine theta. Okay, so why has it not got petals in it? Let me check.
Aren't cosine circles and the sines petals?
Yes, they should be. I'm trying to find the question, so I may have misread the question. To me, I want a petal out of this. I want a 4 petal. So that's what I want. Now I'm going to have to find the original question to see what happened to it. Oh, it had 3 theta in it. Okay, that makes a difference. Evidently. Okay, where's Desmos? I didn't do any diff. Oh, I have to put theta in there. There we go. Do you see the 3 petals after about the 3rd attempt? There we go. Now, we are being asked to find the area of one of these petals. Okay. So we need to find out the range of values of R and also the range of values of any one of these 3 petals. I'm going to pick this one here. Okay. Now, from the center to the furthest point, would you agree that that is 8? So I'm doing 0, R, and 8. Are you happy about the range of R from 0 to 8? Now I'm going to have a guy going down here and a guy going up here for this petal. So what we need to know is what the range in theta is for this petal. Would you agree it's a negative number on this side and the same on that side by just symmetry?
Yeah, it'd be negative 2 pi and 2 pi.
Oh, 2 pi and 2 pi would loop round the circle. That wouldn't give me 1 petal. We have to do whatever that angle there is, right? And we have to do whatever that angle there is. That's the problem. So what is that angle going to be? Right. So the petal I'm trying to draw. Oh, wait a minute. I'm going to go back and show you my writing now, because we've seen what the shape looks like. And this is not as obvious as it might be. Right. That's the petal I'm going to get, right? That one. And 0 to 8 was pretty obvious. What I'm saying here is that the angle that's coming down here and the angle that's going up there, right? That's the ones I need for the range of theta. And while I'm at it, it's 3 theta here. Okay. If you did here to here, wouldn't that be pi upon 2? Agreed? That's theta is 0, that would be pi upon 2. And your temptation would be just to think then negative pi upon 2 plus pi upon 2, but it's not as simple as that. That's what 3 theta generates. So the missing numbers are those. Now, if the question had been a cosine theta, then I would have said pi upon 2, negative pi upon 2, right? I would have went that way. But if it had, let's pick one off the top of my head. Suppose it was 7, I'll do cosines again to keep the shapes the same. If it was cosine that guy, then I would be saying pi upon 2 would be generated by 4 theta, and theta then would be pi upon 8. So that is the bit that's not obvious. Now you want to do the integral. You want to do the double integral that gives you this area. The double integral that gives you this area is just the integral of 1 dr d theta. And my argument for that is that if you imagine this petal being 1 unit high, wouldn't this volume be the same number as the area of the base because the height is 1? Does that make sense? So if you're wondering why that one is there, that's what it is. Now the integral that we have is r equals 0 to r equals 8. And from theta equals negative pi upon 6 to theta equals positive pi upon 6. This guy gets an r dr. And this guy just gets a 1 d theta. Are you happy about the variable splitting? Are we good with that guy?
Yeah, I have a quick question though.
Yes, Terence.
Why not just do it for theta equals 0 to pi over 6 and then double the result? That gets you the area.
I like your thinking. Nothing at all. It would work perfectly and probably would have been a little bit easy. So this guy gets me a half r squared. And this guy gets me theta. And this guy gets me 1/2 times 8 squared, take away nothing. And this guy gets me pi upon 6, take away negative pi upon 6. And that guy gets me half is 64. And this guy gets me 2/6, which is 1/3 pi. And so the final answer is 32/3 pi. So the area of one petal of this
You mean
curve,
32/6 pi?
32/6 to check that and that add together to give me a third. So I do mean 3 or 2/6 if you want. So you put these together, you get 2/6 pi, which I then just converted into 1/3. And
Oh,
this
so you
gives,
just factored out the 32.
yeah. And then I took this and put them together and we're good. Okay, everybody, time to put your last name down. What you were saying a few moments ago, Terence, reminds me of a phrase, there's more than one way to skin a cat. So can you imagine you may have chosen one of the other 2 petals and wouldn't still give you the correct answer. Although setting up the theta values probably would be even trickier for those. That's it. I'll hang about for any questions. Otherwise, bye-bye and I'll see you tomorrow.
Thank you.
Yeah. And I did a really good, I liked the brain joke, Sally. Did you like the brain joke? Rosie, you got a question. What's the question?
Yeah, so
And
when you were
no,
finding-
no. You liked my brain joke first, right?
Oh, of course. It was
Oh,
great.
of course. Okay,
They're
what's the
always
question?
good.
What you got?
So when you were finding the limits of integration for theta, how did you notice that 3 theta equal to pi over 2?
Ah, okay. So right, the guy that looked like that again, right? So I know this angle is 0, and I know this angle is pi upon 2. Great. Oh, you can't see it. So my logic went something like this. So I'm just basically interested in this piece, right? And then symmetry would tell me the other one. So I know that this angle starts at 0, and I know that this angle finishes at pi upon 2. And the formula that I was using had some number, whatever it is, 8 there. So I was going to say, what would happen, right? Or what would I need to get pi upon 2? Well, pi upon 2 would be that guy. To get the vertical angle of pi upon 2, wouldn't I need this fella to be pi upon 2? And that's kind of how I did it. I just realized that 0, well, at the one side, 0 is 3 theta. And so that just told me that it still was 0. And then this piece here was pi upon 2, and 3 theta gives me pi upon 2, and that would happen when theta is pi upon 6. Suppose I had a shape that looked like, just for argument's sake, let's suppose it looked like that, right? So it would be 0 to pi, right? But the formula I was using was a cosine of 2 theta, maybe with 3 and some, right, whatever. Then I would be saying, okay, to get an angle of 0, when you put a theta in that, you get that. And so that would be my starting angle. But if I wanted to get pi, then the other angle I would use would only be that. So if I was trying to do this one, let's say it was generated by that, my angle would be only 0 to pi. So that's kind of how my thought process was working. I know that that angle is pi upon 2, but what value of theta would generate a pi upon 2? Well, when theta is equal to 1/6 pi, then the cosine of 3 theta becomes a cosine of pi upon 2, and it would generate that angle. I'm not sure I did that clearly. Does that make sense yet? I've got another way of looking at it if it doesn't.
So the part of the pedal in the first quadrant,
Mm-hmm.
the radian, I guess, value of x equals 0 is pi over 2. So then pi over 2 equals 3 theta. So then you're dividing the quadrant into a third.
Mm-hmm.
Oh,
Okay, does that help you?
it makes a little more sense now.
Right. So I was going, I'm not sure I should tell you this other way of looking at it in case it puts you off your thought process. Why am I doing that? It's annoying. Thetas and zeros. I keep drawing a 0 and making it a theta just without thinking. Right. Suppose I had a function, and I'm just going to call it 4 theta, right? To get to the y-axis, won't the angle have to be pi upon 2? Great.
Yes.
And I know that that makes 4 theta would have to be pi upon 2.
Correct. So then it's pi over 8 for theta.
Yes.
Okay.
Is that helping?
Yes.
Right. So there's the angle on the axis, and then there's the angle that theta has to be the same number as the angle on the axis.
Uh-huh.
Right. Then we are good.
All right. Thanks for explaining that.